Topics 8.5 and 8.6 should be taken together, and I believe we do present them that way. We're calling a modification of 8.6 A.3. So keep in mind that was what we used to call it, and we're referring to it as this. There's been some changes. So we're going to take a look at our learn. And it ties in logarithmic and exponential equations. Now, the key to all of this is taking some good notes on the formulas and know how to use them, how to substitute data into them. As we do the formulas here, you want to have a good calculator, something like this. And this is a Casio, but it has the needed keys. We need a logarithm key, we need natural logs, we need the letter E, and of course the TI-83s and 84 series, they have them as well. So you need to know how to use these types of calculators with those calculator keys. Before we go on, I want to give you some background information. So in your notes, write the word background. And one of the most used types of logs are called common logs. Now, common logs can be written log all by itself, where there is no base that is showing. When there is no base that is showing, this is a common log, and we can put a 10 there as the base. So the base for common logs is 10. And on your calculator, the key is log. So you'll see that on the key of your calculator. Well, that is the common log, and that is base 10. Now, another one that you'll see on your calculator keys is the natural logs. Now, the natural log is written L.N. And you might say, how come it's not written N.L.? Well, because this is its Latin version of it, Logarithmus naturalis, something like that. Now, the base of natural logs, and they don't write it, is Euler's irrational letter E. So, common logs, base is 10. Natural logs, base is Euler's. Now, there are a number of formulas that we're going to be using, and at this time, carefully write these formulas in your notes, and I'll go over them with you as we go along. So the first one we are to write is this one, which is what is called a continuous compounding interest formula, where A is the future amount, P is the principal, that's the money you're going to put into the system. The R is the rate. Usually it's given as a percent that you need to convert to a decimal, and T is years. Now, E, if you're wondering, approximate value of it is 2.7. Now, notice the use of exponents. Now, another one is just a compounding formula for compound interest, where n is the number of times it's compounded during the year. So let's write this one out. Future amount, that's the same, equals the principal. And then now in parentheses, it's 1 plus the rate. Again, it's given as a percentage, but we convert it to a decimal fraction. Now, n is the number of times it's compounded during the year. Annually, n would be 1. Semi-annually, n would be 2. Quarterly, n would be 4. Monthly, n would be 12. Daily, and they usually qualify this, 365. Now up here, we have n, again, the n that we use here, we have it here, but now it's the product of n times the number of years. So this is continuous compound interest. This is just compound interest. So two different formulas. Now let's go through these others, take some good notes, and these will be part of background. And just pause it here now as we look these over. You want to write this one. This is the formula for decomposition of radium, where T is in centuries now. This is the formula for skin healing, where T is measured in days. Formula used for carbon-14 dating. If you have a little bit of biology background, carbon goes into living systems, so it's on balance, but once it dies, the system is no longer in equilibrium with the environment, and then the amount of carbon-14, which is radioactive, starts to disintegrate and convert to something else, and this can be measured, and they use this often for fossils, and this would be the formula for that. And then this one is Newton's law of cooling. We'll be using this in some examples, where C is the constant temperature of the surrounding medium, and the values A and K depend on the particular object that is cooling. Again, there's some pretty heavy things here, but having the calculator and then the knowledge of logarithms and the use of exponents will help us get our answers. Now, as we get into our first example, label this example 1. They're giving you this formula, y equals y sub O, and then Euler's E, and then the exponent 0.4, and then T is going to be the number of bacteria present after time, which is measured in days. Now, we're starting off with a rather challenging one, but the protocol here is if you get one like this, this is what you want to follow. This is your model for doing it. So there's step 1 that we have here. Now we're looking for the number of days it takes for this to double. Well, this is y sub 0 is sort of the beginning and what your original number would be. So if you want it to double, over here you're going to put 2 y sub 0. Now, they have it written up in the text, but I'm going to go through what they have step by step, and you can follow it step by step. So we have the double of y sub O is 2 y sub O, and the rest is just copied. Now, what we're going to do here is we're going to divide out using algebra y sub o from this side and y sub o from that side. It's a nice thing about algebra. So this just becomes a 1. So now we're left with the 2 equals this. Now, what they're not giving us as background is that we can use logarithms to solve for exponents. So the protocol for this is since this is natural log e, we're going to convert this line here to a natural log problem. We're going to say the natural log of 2, and remember this is at an exponent, is the natural log. Now I'm adding this. When it's written, the base e is there, and this is of e is to this exponent. Well, we had said that this arrangement is actually a 1. And that's what they're showing right over here. Remember, this is of e, and this, we said in the previous lesson, is 1. That's why these two lessons need to be taken together. So this then becomes this, that this part just becomes the exponent, and it equals that. Now, again, the natural log from this part is gone because that's just 1. So we're left with 0.4t equals the natural log of 2. Now, to get t by itself, we're going to divide by 0.4, and that's what we're doing on both sides. Now, here's where you need to put into your calculator the natural log of 2, and then divide it by 0.4, and see if in fact you get this. And I just did that, and I got this rounded off to 2 decimal places. Now, for example 2, be sure to write this up, we're getting sort of an interest one. This is continuously compounded interest. And for that, we're using that special formula, A equals the principal times Euler's E, and it doesn't hurt to write these again, times the rate, exponent rate times the time. So I'll go back to red, and it's just a matter of substitution. So we have A equal our principal, if it's this, is 1,000. It's invested at a rate of 6%. We have Euler's E. 6% we're going to convert to 0.06. And we're wondering what t is. So they're not telling us what t is, but they are telling us what the future amount would be. So I can erase that and put in 5,000. Now, interestingly, we're going to use a similar process to what we had earlier, except it's not double, it's just this. So let me do that one with you as we go along. But again, the protocol is here. We want to solve for the letter T. So step number 1, and I'll go to black. We're going to divide this side by the 1,000. And this side by the 1,000, using a little algebra. So this now becomes a 5. This is gone, and we have E, and then 0.06 t. Now we're going to convert this to its natural log form. So we have the natural log of 5 and the natural log of E. Remember, this is base E, So all of this becomes a 1. So we're now left with natural log of 5 equals 0.06 t. And you might say, well, what do I do now? Well, I'm going to divide, change to black again, both sides by 0.06, just like we did before. And you can try this out. The natural log of 5 divided by 0.06 and round it off should come to 26.82 years to 2 decimal places. Check it out. Again, this is the protocol for doing it, but I don't know if you can see there's sort of a shortcut here. If you knew what this side is going to end up being, you're just going to take the natural log of this and divide it by the rate. But again, this is the protocol. Let's go on. In example 3, we're dealing with the Richter scale, which is used to measure the intensity of earthquakes, which are actually logs. And this is the formula. So they're saying in 1994, the quake measured on the Richter scale 6.7 log of I. Now, since there is no base here by this log, this is a natural log, so this is going to be 10 of I. So we're wondering what that exponent would look like. Well, if we convert this now from its logarithmic form to its exponential form, what is our base here? Our base is 10. What is the exponent of this? Well, the exponent of this is 6.7. And that equals the answer, which is I. So now we are really bringing in what we had in the previous lesson here. Pretty straightforward if you know that conversion. Now, for example 4, reading it carefully, North Beach in 1933 had this on the Richter scale, and the North Ridge that we just spoke of in the previous item was this on the Richter scale, and they want us to compare them. So we set up a little ratio. Now, from chapter 5, you have to know how to dealing with exponents. Remember, when this comes up, this exponent, we just subtract it from this exponent. And it becomes this, and then 10 to this power. When we put that in our calculator, we get about 3.16, rounding it off to 2 decimal places. So again, these are models that you're going to follow should you get examples like this in practice and certify. Now, for example 5, we're dealing with half-life, where there is a deterioration. We talk about radium, which Madame Curie discovered, is a common isotope. Its half-life is 16,000 years. If 10 grams are present today, how many grams will remain in 500 years? Now, the formula we're using for half-life is Y equals y sub O, that is the initial amount, and then E. Now notice our exponents are negative, so a negative KT. And what we want to find out as we substitute into this formula these various things. So our initial amount we said was 10. That's what we're starting off with. We want to see when it gets to be half of that, or in 500 years. And then we have our E. And we know our time is 16. I could put a dot there for multiplication. So we're here. Or we can put that in parentheses too. Now, I don't know if you see something, but this is going to be very similar to what we've done already. So we're going to divide both sides by 10. And they're using 5/10. We could use 0.5, which is 1/2, equals E, and then a negative K, and then 1600. Now we're going to convert this to its natural log form. So natural log of this and natural log of this. Remember, there's an E here. And all of this, we said, becomes a 1. So we now have natural log 0.5 is equal to a negative K times 1600. Now, we want a positive K, so we're going to divide this side by a negative 1600. Divide this side by a negative 1600. And that leaves us with, this becomes a positive, and we're just left with K. And that's what they have here. Now you put this into your calculator. Natural log of 0.5 divided by, then you have to be careful how you put that negative in. And it becomes this. Now we round it off. We raise it up here. And I'll clear this up because their work is still there, which reflects ours. And we see that you'll have about 8.05 grams of radium after 500 years. Again, this is sort of tedious, but you have a model that you can follow to work it. This is our last example. And again, it's example 6. And it's rather English. Newton was English. Suppose that the room temperature is 70 and the temperature of the cup of tea is 150. This has to be Fahrenheit. And when placed on a table, in 5 minutes, the tea cools to 120. How long will it take for the tea to cool to 100? Okay, so what we're going to do, this is the formula we're using. We're going to do substitution with what we know. So the initial temperature here is 150. We don't know what A is. Now, we also don't know what K is right now, but it's times 0. This is starting. T is 0. So notice our exponent is negative k times 0. Well, anything times 0 is 0. So what does our e become when it's e to the 0 power? So this is going to become a 1. So we have 150 equals a. Now, anything to the 0 power is 1. So this is times 1 plus 70. Well, we're going to subtract 70 from both sides, and we get 80. So A is now 80. So we've determined what it would be initially, and then we need to put that into the formula. So we had to do all of that just to figure out what A was. Now that we know what A is, we then rewrite it in the formula, and our new temperature is going to be 120, 80 E to the negative K, and now this is 5 minutes, and the room temperature is 70. Well, we're still going to get rid of that 70 on both sides, and that gives us 50. And then we have 80 E negative K5. We're going to divide both sides by 80. And we have this now as 5/8. Just canceling out these zeros here. And we're going to convert this to its natural log, so we can put that there. Now the natural log of this side I could write it this way. So this here becomes a 1, and we have the natural log of 5/8. I just put that in a parenthesis when you work it, is equal to a negative 5K. So as we do this division, dividing both sides by a negative 5 here, we get that K equals this, and I just verified that using my calculator. So with the work all shown here, I'll get, and we'll follow up. I think you know the protocol now. So we now have our value of K, which is this. We want to solve for T. So we're going to subtract the 70 from both sides, get 30. Divide both sides by 80 and get later the natural log of 3/8 equals this. Now notice this is E here. All of this becomes a 1, and we now have this. So you can figure we're going to divide both sides by this, and they're showing us here. And again, you got to be careful of the signs. Take a moment to pause, and we find out then that T will cool to 100 degrees in about a little less than 11 minutes, but they want you to round to 2 decimal places throughout this. Okay, I will have a homework help on lesson A.3, which used to be our 8.6, and there will be help available for you on this. Okay, I think we're going to be ready For our open notes quiz, we'll do some classwork and then wind this up.